Okay, so today we're demoing a two-wheeled inverted pendulum, and you can see here that the robot is balancing on two wheels here. It's going to use the motors controlling the two wheels to attempt to keep the robot balanced. It's also the controller that I've built for this is going to attempt to keep the robot in the initial position. So if the robot ends up being over here, it's going to drift back towards its initial wheel angle position. So the sensors that we use are the encoders inside of the motors here to sense the wheel angle from both left and right, and also a gyro sensor on the back to tell the body angular velocity. So the way that the program is set up, it uses calibration to you have to set the robot in a stationary position, press the initialize button, and what it's doing now for 15 seconds is calibrating. So it's just taking an average of the gyro sensor values to create an offset value to make sure that you're getting the correct, that you're using the correct angular velocity values from the gyro sensor. And it'll beep when it's done. I guess I didn't start it. It'll beep when it's done. It takes about 15 seconds. Okay, so it beeped. And what I'll demo is that you can actually start it in a completely upright position, or you can start it a little tilted. Either way, it'll gain its balance at the beginning. So I'll start it as it's tilted, and you'll see that here that it's tilted. And press this button here. And it gained its balance. And it's drifting back towards its initial wheel angle. So it's attempting to, like I said, it's attempting to stay at the initial wheel angle, and it's also attempting to stay upright. If I poke it, it'll resist being tipped over, and also resist being taken to this other location. So if I insist that it goes to that location, you can see that it's leaning towards where it wants to be, and then it goes back and returns. I'll do a very abrupt poke, you know. So what we did here is there's two observable states for the control system, which are what I talked about before, the wheel angle and the body angular velocity. So what we had to do was design a Kalman filter to estimate the unobservable states, which is the body angle, and also the wheel angular velocity. And we use Matlab to estimate the feedback gains and the Kalman filter gain. And we implemented that on the robot, and it included a really iterative process to update the noise estimate matrices, and also the weight matrix for the feedback gain. So we started out with the robot balancing, but it was really sporadic movement. It was really overcompensating for trying to balance. It was using a lot of battery. So I tweaked it until, you know, there wasn't very much fluctuation. It's fluctuating here just because it has to always move to balance. But before, it was a really sporadic kind of movement trying to balance. So it's a lot more stable than it used to be. And I can also demo here, if I rotate it a little bit, that it can also, this is a board here, it can also, I'm lifting the board, you can see that it still works. It still works while it's angled. It tipped over there, but I think I gave it too much of an angle, but it still works while it's angled. And then also, because the wheels, the program uses an average of the two wheel angles, the robot can actually function with just one wheel. Obviously, it won't be able to handle as much of a disturbance as with two wheels, but it can still balance. And I'll attempt to demo that right now if I can unplug this. So you can see there I unplugged the right wheel, and it's only using the left wheel. And you can see here if I poke it, it's trying to balance, and it's, instead of moving back and forth, it's just rotating to try to balance because it's just using its left wheel. And it's also attempting to stay in the initial wheel position that the program started at. So yeah, there we go. That's the demo.